All right, how we doing? Cache lab. Excellent. All right, so today we get to talk about exceptional control flow, exceptions and processes. Okay. So exceptional control flow is sort of a meta title that your book is sort of invented to capture a whole bunch of ideas. What they're talking about here basically are a collection of things that capture things that happen only occasionally, that aren't really part of the high-level logic of the program. So processors do one thing, right? They basically fetch, decode, and execute instructions. Boom, 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 boom. This is the normal flow of control for a processor, right? The program counter moves forward, they fetch that instruction, decode it, and execute it. That's sort of the high level what processors do. This is changed by things like jumps and function calls, right? So if I have a jump instruction, right, my jump instruction takes me to a different address. It can skip forward, like you might have on an if statement, or backward, like you might have on a loop. Okay. Function calls also alter this process, right? Because normally you're walking straight forward, and now you can jump basically anywhere, right? Then you execute, and surprisingly enough, you jump right back. And at this point, you guys already know the mechanism by which that happens, right? You already know how that address is pushed and popped from the stack. Okay. So when we think about things like if statements and while loops and switch statements and things like that, and calling functions. These are all things that involve what the program is doing. Things that are knowable in advance, right? But there's also what the book is calling here system state. What happens when a packet shows up in a network, or the user hits Control C, or when these other things in the environment come in out of nowhere, right? You're not scanning for a Control C, it just shows up, right? What happens when these things happen? What happens if you divide by 0, or if you use memory that's not accessible, and so on? Now your program has to react to that, right? So these are things that happen sort of very rarely, but we need to be able to deal with. Hence, we have exceptional control flow. Control flow that handles these exception cases. So there are low-level mechanisms and higher-level mechanisms, right? You guys are familiar with some of the higher-level mechanisms, already, right? For example, you probably have used exceptions in Python, right? How many of you have used exceptions in Python? Okay. Simple form of exceptional control flow. I wonder where the rest of you guys came from. C has a more primitive mechanism called set jump and long jump. Okay. We've talked a little bit about process context switching, right? Switching from one process to another, signals, and so on. There are these lower level things, okay? Exceptions, interrupts, traps. And the idea here is that the user process is doing whatever it's doing according to the logic of your program. Then one of these system things happens. Suddenly, control flow jumps to the system level handler. It handles that particular situation, and then control flow jumps back. Make sense? Okay. And so basically, the handler is a lot like a function call that you didn't happen to call. It like got injected in there into the stream. Okay. So before I dive into this slide, I want to talk a little bit about one thing that's not here. If you think about it, right, we know that right now, if I look at a particular core, right, and your process is running on that core, what is not running on that core? My process, right? Let's ignore hyper-threading for the moment and things like that. My process, right? So is the operating system running on that core when your process is running on that core? No. Right? A lot of us have this view the operating system is like air traffic control or like a police officer in a busy street and can go in and grab things and organize things and say, no, you're dead, right? Whatever it happens to be, right? Get off that runway. But it doesn't really work that way. Because if your processor is on the core, the operating system is not running on that core, right? And think about classic systems that had one core. If a processor was running on that core, the operating system was not. And that introduces one sort of interesting question, which is how do we manage multiple processes where a process owns everything? But it also raises a lot of other interesting questions. For example, if there's the computer and your process is the only one running, what prevents you from reading his files? It's not like the operating system is there, I wonder how that sounds to the guys on the camera. Where's my microphone? We'll try that. How does that sound? Cool. Here, quick, you try. Much better, okay. Just need to do those audio checks for the distance students occasionally. Okay. So something has to give here, right? There has to be some way that even though you sort of own everything right now because you're running, you don't own everything, okay? So processors have at least two modes, okay? At least sort of a user mode and a supervisor mode. And here's how it works. When your process is running, it sort of owns everything except for certain resources, basically actual hardware, okay? Actual I/O devices, okay? Things like that it can't access because the processor is in user mode. And those hardware things, I/O devices, can only be accessed when you're in privilege mode, supervisor mode. Okay? So now the question is, how do we get into supervisor mode? If I give you a lever that says go supervisor mode, you'll pull it and you'll have access to everything. So here's how it works. There is an array of function pointers. Okay? It goes by all sorts of names: the exception table, the interrupt vector table, the trap table. But the bottom line is this: it's an array of function pointers. And the functions that are pointed to by this array are initialized when the operating system boots. In other words, they're trusted code. They're part of the operating system. Okay? And so what happens is, when these prescribed functions run, they run in supervisor mode. Anything else runs in user mode, but when you run these functions, they run in supervisor mode. And that's okay because these functions are trusted. They're part of the operating system. And they'll check to see who's asking before they actually do anything. Does that make sense? They'll enforce those permissions. They'll say, okay, whose file are we trying to access, and who's trying to access it, and what are the rights on that file? And how is it trying to be accessed? Okay? So what's going to happen is, if we want to do something that involves I/O, involves like real devices. In particular, let's think about an example of an open or a close or a read or a write. Okay? Because those are easy examples. Or we want to create a process like a fork, load a new process image in exec. These things all require privilege. And so what we do is we call one of these functions. There's an assembly instruction called a trap that lets us call one of these functions. And so we do our trap, and we say, I want to call function number 6, or function number 7, or function number 8, and then call a trap. And then it executes my trap function, which gives it privilege. And then from there, there's a table of system calls, and it calls the 6th or 7th or 8th system call, whatever one we told it to call. And now it runs with privilege. And now it's running trusted code with privilege that has the ability to enforce those permissions. Do you see how that works? There's this table of special operating system functions that have privilege. A trap executes one of them, called the trap function. And then there's another array that contains your system calls. So if I say trap 6, it's going to run the trap function with an argument of 6, and then that's going to cause the 6th system call, whatever that happens to be, read, write, open, close, fork, whatever it is, in supervisor mode. And now it can check to make sure you have permission to do that before you do that. And then when it's done, that function returns, and this function returns, and when it does, you lose privilege. Because that's the last thing that function does before it leaves. Does that make sense? So now there's nothing you as an end user can do to interact with these devices that are high risk other than this trap. And if you do this trap, then you're accessing a trusted function. Make sense? Yeah.
When you're setting, like, said it was trap 2, it's going to the second spot in the exception table?
Well, so ignore that. I said ignore the slide for a minute. Trap is, there is a table that I'm just saying is the table of privileged functions. Okay, some are called traps, some are called interrupts, some are called exceptions. They have different names, but the bottom line is there is this table, and when you run one of the functions from this table, it does so with privilege. If you as a user want to make a system call, the way you do that is you specify the system call number and then call trap. Trap runs the trap function with an argument of the system call number you want to call, and then it executes that system call. Because there's actually another table that uses of system calls. Does that make sense? Okay. Now, I talked about one case where we use this, right? The case of us as users wanting something to happen with privilege. But there are things where privilege just needs to come up in sort of arbitrary ways. For example, what if one of your processes is trying to access memory? And you dereference a pointer, and the address is bad. Well, at some level, that's going to fail, depending upon what the situation is. Either the memory controller won't be able to handle that address, so it won't be something that's addressable, or it's addressable, but it's not mapped. We know a little bit about virtual memory. We know that we have a certain amount of physical memory, and it's backed up by the ability to use disk to swap. And it's possible what we're looking for is swapped off to disk. Okay? Or it's possible that you're using a bad address. You just have a bad pointer in your code. Right? So one of these things is going on. The program is running. The memory controller is trying to access the addresses it's being fed. And somewhere along the line, right between this code, between this code trying to access this address and actually the memory controller being able to deliver it, there's a problem. Okay. Well, now what happens is it generates an exception. It's called a page fault. It says I can't access that address. Normally, I use the machinery we'll talk about soon enough, right? Page tables to translate this address. Okay, and then we access the address, but I can't. Page fault. So now the operating system starts to run. Because what happens is when a page fault happens, it has this array of exceptions, and it executes the fault handler, which runs with privilege. The fault handler basically is the operating system's page fault handler. And so it says, okay, what's going on with this? Is this address valid? No, it's not valid. It shouldn't be valid. And causes a process to die of a seg fault. Or it says, yes, in fact, this address should be valid, but unfortunately, I swapped that page to disk, so I should fix that. Dear disk, please get me that page and put it over here. And when you're done, let me know. And then it parks that process and runs another one. And then later on, the disk says, okay, I'm done. I copied that page to memory for you. Well, that's an interrupt. That's another trip to a table like this. And now the interrupt goes off. Your process might be in the middle of a printf. But suddenly, this interrupt wire, right, lights up the processor, voltage on it. Hello, interrupt 6, whatever it happens to be for a trap. For the disk interrupt. The interrupt handler runs. It runs with privilege. Okay? And now it says, oh, okay. That disk buffer is ready. Anybody who's waiting for this disk buffer, you're runnable now. And is able to schedule those processes to run. At least as runnable. Does that make sense? And so basically, this is what all these data structures look like. Whether it's handling a trap or an exception or a fault, it's an array of functions that are part of the function pointers, where each function pointer points to a function, those functions being part of the operating system, so they're trusted. So they can enforce protections. Okay? All right. Here's an example of a trap in Intel assembly. You see INT, they call it interrupt. Okay? And so this is a trap for an open. Interrupt 80. Okay. Here's a fault example. Here you can see we're accessing some array. array element 500 equals 13. Now let's assume that that portion of the user's memory is currently swapped out to disk. So now the operating system needs to fix that problem. And so our standard little triangle here, the process tries to do the move, but when the memory management tries to address that, it can't. MMU can't handle that address, so it generates the page fault. The operating system then loads that page into memory and returns, and we proceed with the move. This is a little oversimplified because the operating system, this can't be loaded from memory immediately. The operating system will park the process, make it block it, run some other process, and come back to it later. But that's basically the flow. Invalid memory reference. My array is 1,000. This is 5,000. This is bigger than the size of my array. Oops. So move generates a page fault. The operating system figures out this is an invalid address. The operating system then signals the process. Tells the process to die. Gets a sig-seg-v. You guys know sig-seg-v. Okay. Here's a little piece, an excerpt of the exception table on the 32-bit, architecture. You can see that 0 is a divide error, 13 is a GPF, general protection fault, 14 is a page fault, 18 is a machine check, 32 through 127 are operating system defined. Decimal 120, hex 80 is a system call. 129 through 255 are also system defined. Okay. I've used the word process and program a lot. Let's think about what the two mean. A program is something written in advance, right? Program. All right? It's the code that you write technically. You write the program. Okay? You don't run the program except perhaps in interpreted languages like Python or Ruby or Perl. Right? Normally you run an executable file, right? So normally I have my program, I compile it, right? I generate some executable. This executable process image is loaded into memory, and then we begin executing that process image. So the process is the live version of the program that we have running. We have the program, we have the executable, and then we have what's actually running. That's the process. The cool thing about processes is that they have two things, right? They have the actual code that's running, right? And they have their own address space, their own virtual memory, which is really nice. So now the question is, how does this actually work? Sometimes we talk about things being concurrent, okay, versus sequential. All right? Well, we have processor sharing, right? Let's say for a moment we have one of the older systems that has just one core. And I have a whole bunch of processes on that system. It wouldn't make sense for me to run one process until it was done, because what would happen is that process would run on the processor for a while, and then it would need I/O. It wouldn't need the processor anymore. It would be waiting for you to provide input, or waiting for the network to provide input, or waiting for the disk to provide input, right? And then eventually it gets the I/O it needs, it processes some more, and then maybe it needs to write stuff out. And now it's waiting for the network, or waiting for the terminal, or waiting for the disk, right? So you have this processor I/O burst cycle that classically looks like read input, process it, write output. And if I have only one process running at a time, most of my resources are wasted because it's reading, processing, or writing. It's not doing all three at the same time. Yet if I load, for example, 3 processes, they could all be in a different phase at the same time. So one process could be reading, one process could be writing, one process could be, processing, right? You could be reading from the network, you could be writing to the disk. You could be computing some things. And now we have all of our resources in play. So to do this, we need to do processor sharing. We need to be able to rotate these processes, multitask, if you will. Okay? This generates what we call concurrency. Because your process runs for a while, and now my process runs, and now your process runs, and now my process runs, and your process runs, and my process runs. So we're both getting interrupted. In many cases, this is benign, but in some cases, it's really not benign, right? You can imagine a situation where there are too many cooks in the kitchen, right? Where one process is reading some data and writing to a file. Another process is reading some other data and writing to the same file. And now the writes get merged together. Because you go, and then 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 you go. And the resulting process is nonsensical. The resulting file is nonsensical. Because the bits are all merged together. Does that make sense? So when we have concurrent processes, that's a problem. In modern systems that have multiple cores, right, we can actually have true parallelism. Two things actually happening at the same time. Older systems, we only had one core, we didn't have true parallelism, but we had this interleaving that gave us concurrency anyway. Okay. If we think about what it looks like when we switch from one process to another, it's something we call a context switch. A context switch. Basically, there's this really simple I/O device. It's a timer. Tick, 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 interrupt. Tick, 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 interrupt. Tick, 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 interrupt. That's all it does. As part of the initialization process, as part of the boot process, you program the timer. You say, give me an interrupt every 10 milliseconds or every 100 milliseconds, whatever you want. And that's all it does. It counts backward and generates an interrupt. And counts backward some more and generates an interrupt. That interrupt has a handler. Right? So when that interrupt goes off, the processor's interrupt wire gets lit up. The processor says, OK, time for me to handle interrupt 4. It executes the handler for interrupt 4. OK, whatever interrupt that happens to be. I don't remember, actually. That handler runs with privilege. That handler is the operating system scheduler. The operating system scheduler says, OK, what process is running right now? What process should be running right now? Who's waited the longest? It takes the running process and blocks it. Makes copies of its registers and saves the process. It takes some other process and restores it. It takes its registers and restores them. And now we return from the context switch, but the instance of the return is a different process. You were blocked. You were restored. Now you're unblocked. Okay? So each process that returns is returning from being blocked, right? Okay. And that's what this shows. We start out in user mode till we get an interrupt, in which case we end up in one of those privileged functions. It runs, finishes up, and then we transition back into user code. Run some more. All right. Now, processes. If I want to create a new process in Unix, and this is going to sound silly, but it is what it is. The traditional way of doing that is by creating a brand new copy of myself. Basically cloning a process. So if I want to create a process, the only thing I can do is clone myself. Bleep. Now there are two of me. Oops. Then what I'm going to do is I'm going to morph one of me into something else. But I'm going to start out by cloning myself. And that's what fork does. So one process starts out, and it calls fork, and now I have two processes. Each one thinks it's in the middle of a fork, right? Because they were cloned when they were in the middle of the fork. Each one now returns. They're basically exact copies of each other, except for the fact that the original process, when its fork returns, it returns the process ID of the child, or new process. The child process, when the fork there, returns 0 as the process ID. Child returns 0, parent returns the child's PID. Does that make sense? This is helpful to us because it lets us distinguish the two. And this is important because I may want to leave the parent alone, and I may actually want to turn that child into something else. One way I can make the child do something different than the parent is just through the simple use of an if statement. I call fork, and now I ask the question, am I the parent or the child? Am I the original or the copy? If the process's ID is 0, am I the original or the copy? The process ID is 0, hello from the child, I'm the copy. If the process ID is not 0, that means it's a real PID, like 5417 or something. That means I'm the parent. And so now the parent and child can live different lives because one's an if case and one's an else case. You're smiling. You're glad you live a different life than your parent. Those two are looking at each other going, Okay, I want a front-facing camera one day, and I have joysticks for it. All right. Okay. We don't know which runs first, the parent or the child. There is no guarantee. So if I call fork, it's not the case that the parent always runs first or the child always runs first. We should assume that we do not know. If our code requires one or the other, right, we need to do something to enforce that because the system does not make us that guarantee. Okay. Here we have a variable called x. X equals 1. When the process is forked, there are two different copies of x. There's the copy of x in the parent, there's the copy of x in the child. Neat. You see that? Each has an x, but not the same x. Okay. What happens if I have a fork followed by a fork? Well, remember, this turns out to be a tree. When I call the first fork, I went from having one process to having two. Now, each of those processes calls fork again, giving me two more. Make sense? So we can see that here, where I print out level 0, then I call fork. Now I have two processes at level 1. Okay? Now each of those calls fork. And I have four processes at the next level. Bye. Yeah?
You said that a process is an instance of a program, a running program. Can you just explain what that means?
So the standard phrase is a process is an instance of a program in execution. What that means is when you write a program, you specify how something should act when it runs. The process is an instance or one of a program. The program defines the behavior of the process, but the process is the running instance or thing that's executing that program.
So it's when you execute your code.
When you execute your code, yes. And the process is an operating system sort of abstraction of that. Sometimes captured in a data structure called a task struct or a process, PCB, process control block. Well, what if I add a level? Unsurprising. Okay? Now this one gets slightly interesting because I have a fork which generates a parent and child, but I only fork in the parent. So level 0 continues on, right? Meep. And that's the parent forking and then doing by. Meanwhile, the child prints out level 1. Excuse me. The parent prints out level 0, then calls fork. Now I have two processes. Okay? If fork is not equal to 0, that's going to be the parent. The parent now prints out level 1. Okay? Whereas the child prints out by. Now the parent calls fork, and I do it again. The parent prints out by, the child calls fork. And now each the parent and the child print out by. Okay. In this example, I just layered in another layer of nesting. If fork equals 0, in other words, if it's the child. In this case, I'm only forking in the child, not in the parent. And so I get a stair-step look. Okay. When a process ends, right, we call exit. We can pass it an exit code. Although exit takes an integer type, and exit code should be between 0 and 255. Okay? Exit codes higher than that are not valid. And we'll see why shortly. The answer is the higher order bits are used for other things. Okay? You can use @exit to register a function to be called at exit. So you can say @exit foo. Okay? And that captures the need, right? That solves the problem not needing an exit everywhere you need it. Okay, yeah.
When is it appropriate to not give 0 to exit?
So in general, the way of thinking of this is that there is one way to succeed and many ways to fail. Right? That's pretty true in life, isn't it? And so if you look at your numbers, it's really easy to tell 0 from not 0. And there's one zero and many not zeros. So what do you think we use for success? Zero. Because there's one way to succeed, many ways to fail. Easy to test for zero or not zero. And so for the failure cases, we use non-zero because it lets us be not zero, which is easy to test for, and gives us information as to what type of failure we had. Does that make sense?
Yeah, I guess my question was like, how are we defining success? Like,
if the user asks us to do something,
Yeah.
and we can, we return zero.
okay.
We can't, we try to explain why. Does that answer your question?
So my example is in the CSAPP wrapper code that you guys provide. You guys have a function called Unix error
Okay.
that says there was an error and calls exit 0. That feels like a failure to me, and I'm wondering why that's a 0.
So it probably should be. The question is, the suggestion is that in the books there's an error handler that returns 0. And does it exit or return?
Exit.
That exits with the code 0.
Yeah.
And why does it exit with the code 0 instead of some other code? The answer is I don't know.
Okay.
That does sound wrong.
Okay.
Okay. Now, this is going to be strange. When processes in a Unix system die, they don't actually get buried. I know this is surprising to you. But since you can't bury a process for so many reasons, it becomes a zombie. When a process exits or dies in any other way, right, it becomes a zombie. It loses a bunch of its resources, but a shell of its former self stays around. And it stays around, perhaps haunting your system performance, until it is reaped. I am not making up this terminology. Processes that exist after they die and before they're reaped, they're known as zombies. Collecting the shell of a process is known as reaping it. Okay? Why is it that we have zombies and reap processes? Why don't things just get dead and buried? The answer is this. Sometimes when a process dies, we want some information about how it came to be dead. Okay? If one of you died, your parents would probably want to know how you came to become dead. Everybody agree? Okay. And so what happens is, a dead process stays a zombie until the parent reaps it. You're acting like this doesn't make sense. Yes?
An example is that when we die, our parents would want to know what happened to us.
Yes.
We don't become zombies when we die, so why would those become
How do you know?
empirical evidence?
They could just be well-behaved zombies hiding in the shadows.
That's fair.
Okay. So when a process dies, it becomes a zombie. What this means that it loses most of its resources, but a shadow of its former self hangs around just for the purpose of letting the parent know what happened. When a parent actually collects that data structure, need it or not, that's called reaping the process. Okay? Or reaping the zombie. Okay? The system call that does that is called wait, or another one called waitpid. Okay. So here we have something that forks off a child and then enters an infinite while loop. The infinite while loop is keeping the parent alive. Okay. And then we can come over here and we can take a look at the process status, and we see that in this particular version of Linux they call it defunct. But in many versions of Linux they call it zombies. And if you actually do the version where you show process state as a single letter, it still shows a Z. And that's why it's a Z. It's a zombie. It's not a D for defunct. Okay? Okay. So why do we need that while loop? Well, this raises an interesting question. What happens if a parent outlives its child? I mean, orphans are sad. But zombie orphans are even more sad. Right? I mean, imagine that you have the misfortune to become a zombie and then are orphaned. Or you're an orphan and then become a zombie. In either case, you're an orphan zombie. There's no parent around to reap you. We all agree? So now you're wandering the Unix system, which is probably pretty boring, forever half dead. But that's okay. Because Unix is a charitable world. It is. We have a solution to orphan processes. And it is not an orphanage. So Annie will not sing. Okay? The answer to orphan processes is obviously that we reparent them. And we reparent them to a kind and gentle and gentle and long-lived process that will always be around to reap them. So there's this process called init. And when the system first starts up, the init process starts up and then forks a bunch of copies of itself and then turns them into, using something we'll learn about called exec, all of your initial system services. And then once your system is running and it doesn't die, instead it sits there in a loop around a wait. And so it spends the rest of its life reaping dead processes. Because a process gets reparented to a init, and a init reaps it. Another process gets reparented to a init, and a init reaps it. A init sits there and waits in a wait PID, and then a process shows up and it reaps it. Does that make sense? So when a process becomes an orphan zombie, it gets reparented to a init, and then a init will reap it. Thus, we don't have a world of zombies. Okay. Yeah.
How do we reparent something?
You can't reparent something. The Unix system will.
Okay.
So when the Unix system I have to look at the deals. But if the Unix system basically, if you die, and the Unix system is in the process of cleaning you up, and it sees that you're an orphan,
It walks around yelling out, bring out your...
it reassigns you to the init process. Actually, I think what happens, technically speaking, is when a process dies, all of its children are assigned at that point in time to init. And then they're in the right place should they die. Does that make sense?
Yeah.
Okay, you're welcome. So, wait is a system call that at some level waits for a process to end. So I fork off some process, and then I call wait, and I block until it ends. Okay? And then we see it wait takes one variable, a pointer to an integer. So I allocate some integer, I pass in a pointer to this integer, and then when wait reaps this process, I told you that the reason we kept this zombie around was to keep a little bit of information around, right? It copies that information into that integer. The bits in that integer have different meanings, and so it flips some on and some off to capture the meaning of the various fields. And now, in this integer called child status, we have the status of the child. Okay? It's bitwise defined, right? So we don't want to parse it ourselves. Instead, there are some functions defined in wait.h that let us do that. And we'll see an example shortly. So wait does two things, right? One, it blocks until the process, until any child, okay, until any child is ready to be reaped. Okay? And I guess there are two conditions where it returns, right? Three conditions where it returns. One, a child died. Okay, and now it can reap the child. Two, a child was suspended. Okay? Or three, an interrupt came in, a signal came in while the wait was running, and that causes a system call to return immediately. Okay? If a signal comes in while you're in a system call, that's handled immediately. So here's an example. Right? We have our integer child status. We call fork. We have a wait passing in the address of child status. When child is done, the bits describing it are saved into child status, and wait reaps it. Until the child is done, we sit there in the wait. It blocks. I told you, yeah.
So in that last example, if the child process ran completely and terminated before the parent even got to wait,
Yes.
would it just like wait and some place for the parent to get to wait.
Right, because what would happen if that child died before the parent got to waiting? That's okay, because the child is now a zombie. That just means that the zombie will have a little longer of a lifetime.
Okay.
Then when the parent gets to wait, it'll check for that zombie. Does that make sense? And we'll actually learn the details of how that happens. Okay? I told you that when it comes to interpreting the child status, you shouldn't try to parse out the bits by yourself. You should use macros, like W if exited, with exited. This will test the child status to see if it indicates that the child exited. Okay? If it exited, it'll have an exited status, a number between 0 and 255. 0 being success, 1 through 255 being some failure code. And now I can parse out that number from the bigger integer. Yeah?
Where do we get the macros from?
Those are defined in wait.h. Question is, where are the macros from? They come from wait.h. Waitpid or waitpid is a much more powerful version, much more flexible version, I should say, of wait. Okay? They're both the same system call underneath, they're just two different interfaces. Wait lets us specify exactly, waitpid lets us specify exactly which process we want to wait for. Wait by itself waits for any child. The first child to change state, wait will pick up. Waitpid lets us wait for a specific child. Okay? Or a group of children. Okay? So we pass in what we want to wait for. Which process? Okay. That can be 0 for any. That can also be a negative process ID number for a process group ID, and so on. Child status, the same as before. And then there's this thing called flags. Right now we have a 0 there, which means no flags. The only flag that we're likely to use, at least in this class, is W no hang. If W no hang is specified as a flag, wait will not wait. It'll check to see if there's information available now and grab it, but if not, it'll return anyway. It will not block. Okay? And we'll see why that turns out to be useful. So a waitpid with a 0 here and a 0 here is basically equivalent to a wait. Now, cloning processes are tons of fun, but eventually we actually just want to run another program. And we do this with any one of several different function calls in the exec family. Exec loads a process image. In other words, I've cloned myself. But if I don't want to clone, what I can do is turn one of those clones into another process by loading that process into memory, or in more modern operating systems, just mapping that disk into memory. And by doing that, I've converted the existing process into a new process. So basically what exec does is throws away the process state and reloads it. So I fork to create a new process, and then exec to turn this process into a new one, into what I want it to be. Okay. Exec VE is one form of exec. V says it wants the arguments in so-called verbose mode. E says it should take the environment via pointer. The environment of a process is basically defined by a whole bunch of so-called environment variables. These things that are variable name equals value tuples. Okay? And they're just strings. Do a setenv or a getenv, or a set or or a set depending on which shell you have, and you'll see your environment variables. So exec VE, we provide the file name of the file that we want to exec. We provide the arguments like ls space minus L, right? And then we provide the environment, one of these name equals value strings. Here's an example. I want to run some program, that passing in at the command line is argv of 0. I exec VE argv of 0. Okay. By convention, the 0th argument is the name of the process. Now I pass in the whole array of arguments, and now I pass in the environment. Okay? Now, here's a trick. Do you see anywhere there where it tells you how many arguments there are? Anywhere? No. The way it knows is that it walks through that argv array. Is this null? No. Good. It's an argument. Is this null? No. Good. It's an argument. Is this null? Good. No. It's an argument, right? It walks through and it knows how big a pointer is and looks and says, is this pointer 0? If it's not, it's an argument. Pointer to an argument. When it gets to the point where the argument is 0, it knows it's done. So your argv array has to be null terminated. If you want to pass 5 arguments, argv of 0 plus 4 more, right? You actually need to have one more space than that for the null. You need to have your argv of 0, your argv of 1, argv of 2, argv of 3, argv of 4, and then your last argument has to be null. Does that make sense? Any questions?
Is the environment array also, the environment variable array also null terminated?
Is the environment variable array also null terminated? The environment variable array is also null terminated, yes, because again, there's no argument there that tells us how long it is. Does that make sense?
Yep.
Okay. There are several forms of exec. Another form of exec has an L instead of a V, meaning long. For that version of the function, it's slightly confusing, but you actually pass the arguments to your program as arguments to exec. So it's exec, argv of 0, argv of 1, argv of 2, argv of 3, argv of 4, argv of 5, argv of 6, and so on. All is arguments to exec, followed by a null, for exactly the same reason. So argv is just flattened out. Yeah?
So the first argument to exec is the name of the process. Where
Yes.
does it have a list of all the processes? Like, is that?
That's going to be, the argv of 0 is going to be like /bin/ls.
Okay, so it's just the system.
Yes, it's going to reference the file system at that point. Yes?
Can you go over what the environment variable is?
Yeah, so the environment variable has things like your path. Like if you move your path, like when I run ls, where does it find ls? It looks first in bin, then user local bin, and so on. Or the path to your, for your compiler, the path for your libraries. Things like that are generally environment variables. What your home directory is. Does that answer your question? You sure?
Yeah, just one, I know, you would never really, as a programmer, you would never really use it, but, what does exec use it for?
Use environment variables?
Yeah.
Every process has an environment. Okay? And so it could be empty, it could be not empty. The question is, do we want that process to get some default environment, or do we want to provide it ourselves? Does that make sense? And the default environment, I think, is inherited, but don't hold me to that. Okay. Oh. Wow, I thought we were going a little farther today. Guess not. Okay. So let's just walk through what we've covered today. We've covered exceptions, right? The thing to keep in mind about exceptions, right, about that process is that the processor has this dual mode operation, at least dual mode operation, between privilege mode, which is sometimes called supervisor mode, and user mode. And the only way into supervisor mode is via one of these functions. And these functions are put there at, when the operating system is booted, they're operating system codes, they're trusted. Okay? When one of these things runs, it returns back to where it was before. So if I run, if I have an exception, right, when the exception's done, the user code's going to run again. Right? If I make a system call, when the system call returns, it's going to pick up where it left off. Okay. Processes, right? They're created by cloning, right? The system call that does that is called fork. Fork is the traditional name of the system call. But the underlying actual name of the system call might be different. That is to say, fork is the name in the API, but the operating system may implement that API slightly differently. In Linux, for example, the actual system call is called clone. And the actual system call is much more powerful. You can determine whether or not you want a new stack, or a copy of the old stack, or a reference to the old stack, things like that. But when you call fork, it calls clone with the right parameters to make it act like a fork, giving you a new copy of the stack, and a new copy of the heap, and all that good stuff. Now, think about this. Nominally, when I call fork, I create a copy of a process, right? Nominally, I have to copy all of its memory, right? Actually copy it. That's the traditional way a fork is implemented, but it's really slow, right? Because I have to make a copy of a whole process before it can run. One thing they do in modern forks to make it faster is called copy on write, or COW. And what this says basically is it creates the new process, but they share the same memory. The memory is just marked read-only. And then when either any process tries to write to a part of it, that part or page gets cloned. So instead of doing it all at once, it does it as needed. And that minimizes the initial delay. It's called a copy on write fork. It's especially nice if right after the copy on write fork, you intend to call exec. Because what does exec do? Exec throws away the old pages to load new pages, right? It's loading a new process image. So it doesn't make sense to copy a whole process image just to call exec. And most forks in the universe probably are followed exactly by an exec. So we're wasting time to make a copy of something that we're just going to throw away. Okay? Modern systems actually have something else called a V-fork, or virtual fork. And the idea behind a V-fork is they don't even bother with copy on write. They just let the two processes literally share the same page tables, writable. Because otherwise they have to go through and mark them all read-only. So the parent and child actually share everything. And then the child calls exec. Hopefully before messing up the parent. But if the child starts to change variables, they're actually still the parent's variables. Because they were just shared. And so in general, the only safe thing to do after a V-fork is call exec. Replace the process image, and then you now have two independent processes again. Okay. We spawn a process with a fork or a V-fork. When process completes, they call exit. We reap the state of a process, and we can get the exit status among other things using wait or waitpid. And if we want to load and run a separate process image, we can use exec VE or exec LE or something like that, one of the exec family calls. In the old days, when we called exec, it literally copied that thing into memory. These days, it actually doesn't. It doesn't call memory mapping it. Basically, it says, assume that this file over here is in memory, but don't actually read it into memory yet. Treat it like it's memory that's been swapped out and read it as you need it. Okay. It's actually the case that it also allows the same file to be shared by multiple processes, since the code can be, right? The code isn't different. If we have 1,000 copies of LS, the code section for all copies of LS is the same. And so the modern version of exec lets that be shared. Make sense? Any questions, anybody? Yeah.
Wait just waits for one child to die, right?
Any child.
It doesn't matter which.
Yeah, die or become suspended.
Okay.
Yeah.
So if you just call wait and you haven't forked any children, is that just the same as an infinite loop?
If you call wait and you haven't forked any children, it knows there are no children, so it returns a code of -1.
Okay.
If you call waitpid and there are no children, it'll return -1. If there are children, but you have the flag W no hang, so it won't wait, it actually returns a 0, telling you there are children, but they're not ripe yet. Does that make sense?
Yeah.
Okay. Any other questions? Thanks, everybody. Have a great evening.